At this point, we've probably all pretty much accepted that the speed of an electromagnetic wave can be written as v equals omega over k. And for plane waves, and in general, waves of infinite extent, that's the end of the story. But soon we're going to be dealing with more localized waves, and we're going to discover that there are actually two different kinds of wave speed. Let's troll on over to a relevant applet and see what we can see. Alright, so here we have a representation of a sine wave that's modulated by some broader envelope. So in addition to that sine wave, we have some overall function here that's changing it from a plane wave to a series of pulses. And this localization leads to the possibility of there being more than one relevant velocity. Let me go ahead and fire this up. Alright, so there's that plane wave trucking forward under that envelope. You'll notice that the big envelope isn't really moving, it's just that sinusoidal wave train moving under it. Take note of the red dot, which is showing you how that underneath sine wave is propagating. And take note of the green dots, which are showing you the nodes in that larger pattern. Alright, so now I'm sending the entire wave train forward. The red and green dots are actually overlapping because the pulse envelope is moving at the same speed as that underlying sine wave. This, however, is what pulses tend to look like in practice. The speed of the overall envelope and the speed of the sine wave underneath are not the same. We call the speed of the underneath sine wave, indicated by the speed of the red dot, the phase velocity, and we call the speed of the overall pattern, the speed of the individual pulses, indicated by the green dot, the group velocity. The group velocity, the velocity of the green dot, is what we think of as the actual velocity of the wave, because it's that pulse that carries energy and information. Underneath it, there's that sine pattern that may be moving at some other speed, but that turns out not to be relevant in terribly many cases, though when it is relevant, it's very relevant. And there's all sorts of different combinations you can have. Here's one where the phase velocity is 0 and the group velocity is greater than 0. Here's one that kind of blows my mind. The phase velocity is negative. That underneath sine function is propagating to the left, but the pulse train is propagating to the right. Here's a positive phase velocity and a negative group velocity. And let's return to this one here where the phase velocity is greater than the group velocity. Okay, so to sum that up, we have two velocities now, one a group velocity and one a phase velocity. The phase velocity is actually what's always going to be omega over k. Group velocity is given by something different, and we might take the opportunity to prove it in the homework, but for now, I'll just tell you that group velocity is d omega dk, which gives us yet another motivation to find the dispersion relation for some wave. If you can find omega in terms of k, or frequency in terms of wavelength, you'll be able to take that derivative and find out how fast the actual groups are moving. Note again that the group velocity is the most physically relevant velocity, and it's actually the only one that's limited to c, because it's the one that defines the propagation of energy or information. Phase velocity can, and often does, exceed c. And it's in the chapter on waveguides that we'll first see this explicitly.